Now.
Right. I will just jump in front of it quickly.
Okay. Hello, everyone. My name is Alex, and I've been interested in scientific computing for a while because, believe it or not, I actually wanted to be a physicist at first, but then I saw how hard it is to do that, so I decided to get into programming instead. But this is a nice way to get back into it, and the topic is Q# and Azure Quantum. Notice how Microsoft loves putting sharp languages, we have C# and F#. Now for quantum we have Q#. So let's continue on. So what are they actually? So Azure Quantum is a service that was created by Microsoft and accessible on Azure that provides people with access to quantum simulators and real quantum computers and all the other tools they need for quantum development. And Q# is a language they created just for quantum programming, and so why go through all this effort just to make a quantum computer and create software for it? Well, there's a whole bunch of applications that this is actually good for, and a lot of them are actually pretty good. And quantum chemistry and material simulation, and also protein folding and molecular modeling research, as well as optimization and search problems. Think traveling salesman, pathfinding, that sort of thing. And the most infamous application for quantum research is RSA encryption cracking. Which is why the NSA looked at using quantum computers. So they actually give you a whole bunch of a few different ways to use Q# and the benefits of Microsoft Azure and Microsoft Quantum. So for Visual Studio Code, they have the Microsoft Quantum Development Kit, which I'll show you when we get to the demo. That's an extension on Visual Studio Code, and then it's also accessible through Python with Jupyter Notebooks. And then also we have the web-based solutions in Azure Quantum. So you don't need to install anything, just run it. So the basics is I kind of find Q# similar to C# and F#. Probably because it's a Microsoft product. Although we have the normal integers, floats, those types of data types, this one has this special data type called a qubit, and that's where the magic happens essentially. And on the hardware level, it uses quantum gates to perform various operations on the qubits, and I'll show you how exactly that looks like in the demo. Okay, so qubits, they're actually a primitive built into Q#, and yeah, and they're pretty straightforward to define. However, the one catch for using them is that you have to reset them right before you release the qubit. If not, you'll get an error. And then the results type is how you get your measurement from the qubit, and it's often used as a return type in Q#. Okay, so operations. So these are what Q#'s equivalent of functions and procedures are, and just like C#, you do need a main operation. But if you need to use like a different operation for your main operation, then you can actually use the entry point decorator to do that. So it is pretty flexible. So like I said, quantum gates are on the hardware level is how operations are done in qubits, and they have operations within Q# in order to do them. So that's how you can run your quantum code. And then quantum development kit, like I said, is an extension that you install onto Visual Studio Code, and has some neat features right out of the box. It has like a built-in quantum simulator they can run your Q# code on, and as well as give you like a diagram of the quantum circuit, and also show you what the results look like in the histogram, which is like what quantum developers use in some situations. Yeah, like I said, it can be run locally. Yeah, it is idealized so there's no noise. It acts like a perfect quantum computer, and the practical limit of like the amount of qubits you can have in a simulator is about 30, because at that point you need like a supercomputer in order to simulate that, and at that point you would need to just use a real quantum computer for computation. And to facilitate all of this, there's a special service in Microsoft Azure called Azure Quantum, and it's a cloud service for running quantum programs. And you can run on simulators or send it to real quantum hardware. And However, the execution of Unreal hardware depends on provider availability and configuration. And since it is a Azure service, you need a Azure account and a Quantum workspace in order to use it. So a Quantum workspace is a Azure resource container used by Azure Quantum, and it groups all your Quantum jobs, quotas, and results. And this is what you need in order to submit your jobs and do pretty much everything. And then that's it for the slides. I just yeah, I didn't want to make it like overwhelming, so I try to keep this short and sweet. So do you have any more questions before we go over to the demo? Yes.
When you said the QDK is ran locally, you mean local on the machine or local through the random?
Yeah, local on the machine.
Is there any, between the three different things, the QDK on code or Jupyter Notebooks or the web-based, does any of them have a plus over the other or something to that effect?
Yeah, for like the local install, it's mostly just like a personal preference. But yeah, I think they would prefer you to use the QDK on Visual Studio Code for local stuff. But then also Azure Quantum is used for if you don't want to install anything, do everything on the web. Okay, if that's it, I'm going over to the demo. So here's my quick,
Do we need to dim the lights?
yeah, that'll be
Yeah.
better.
Which one is it? Okay. Is that good, or you want the back ones off too?
Alright, yeah, so this is a basic simulation or program that you would use. This is kind of the quantum equivalent of the hello world. So what we're doing is, here's the main operation. So we're creating a qubit, then we're using a operation on the qubit, which is this one of the H. It's known as the Hadamard gate, and puts in a superposition. And then in order to get something out of the results, we measure it with this M operation and set equal to a result. Then we reset this qubit, then return the result. So let me quickly show you how it looks to run. So notice it says 0. So that's the one of the states. Histogram. Yeah, so this allows you to do multiple shots at the same time, so you can see we got a little bit more in the zero results this time than one, which is interesting. Estimate, yeah, this basically shows you how much it would cost computationally or do it debug. Yeah, that's what it says. But I'm not gonna go into it because, yeah, it might confuse you. I'm trying to just introduce you to it real quick. And circuit, this is basically the circuit diagram of how it works. So here's our qubit right there, and it's represented as a line. So all these boxes right here are the operations we're doing. So had them are, and then we're measuring it, and then we're
Alex,
yeah.
can you collapse the Explorer on the
Yeah,
side?
sure.
You can see the rest of it a little better. There you go.
Yeah.
Alex,
Yeah.
what does the reset do before releasing?
Oh, it resets the qubit to like the default state because like in real quantum computers you need to like reset your qubits so that the next job can use them correctly, and they specifically require you in order to use it. Let me try to comment
Kinda like freeing up a
this out.
variable.
Right. So almost like a static,
It-
Yeah.
a static
That's-
variable.
It sets it back to what it was at line 5 when it was supposed to allocate it. That's what it sounds like.
Yeah, it's releasing in that variable in a sense, but in I think a quantum realm, you're actually setting an actual qubit into a superposition, so you're releasing that actual physical qubit.
Yeah, because the result would measure it,
Yeah.
which would lock it into a specific.
That's the error you would get if you got rid of the reset.
So, yeah, it's not like you don't have automatic garbage collection, so you have to go back and manually release.
Release it.
Yeah.
Yeah.
Something like C++, like you allocate memory, you have to re-release it, or you just have that memory allocated the whole time.
Yeah. Try and ignore C++.
Yeah. Most people do.
Yeah.
Yeah, I have a few more examples. I'm going to share, which is why I had the so example 2. Yeah, I'm gonna close. Yeah, I had it. Example 2. So yeah, so this one is a little bit more complicated. So we're doing 2 qubits this time, and we're doing the Hadamard gate on the first one. Then we're using CNOT and in the vocabulary of quantum science, entangling these two qubits, and then we're using dumb machine in order to show the state, and then we're measuring it down here, both of them at the same time. And yeah, just scroll down.
So is dump machine dumping this current state of the machine? Like,
Oh.
because we didn't use that in the first Hello World, did we?
They weren't entangled.
True.
Yeah.
There was only one.
Okay.
Yeah.
So we're resetting both and returning the results of the two results that we got. Let's run it. And yeah, here's what the output of the machine looks. So what it's saying is that we have 50% chance of them both being 1 and 50% chance of both being 0. So in this case, we got 1 and 1. Let's do the histogram.
Now, real quick, the basis amplitude table, is that the dump machine part?
Yes.
Okay. So that's just telling you for these two particular qubits, this is the whole basically true false table in this case. If we had 3 qubits, it would look different because there would be a different set of probabilities, especially if you entangled all 3 or if you entangled just 2 of the 3.
Why? I was gonna ask, why is it only 0, 0, 0, 0, 1, 1?
Because they're entangled. So when
one state forces the other.
correct.
Okay.
Yeah.
Yeah, he entangled Q2 and Q1. So whatever Q1 is, Q2 will automatically follow.
Okay, so no mixed states.
Correct. That's why I was saying if we had 3 qubits and then you entangled like 2 of them,
I see.
you'd probably get a bigger machine when you dumped it because then you'd have a lot more probabilities.
Got
And if you can't tell, we're all geeks in this room.
Alright, yeah, so this one's exactly the same as the first one, but I just wanted to show you this one quick change. So I used the entry point decorator this time. So you notice how I've named my operation measure 1 qubit, and it's not main, so I used the add entry point decorator up there, so that it knows that this is supposed to be treated as the main operation.
But then you could theoretically use it as a library and call it from somewhere else with its namespace, and it knows where to start from.
Yes.
Oh, good catch. You can see that.
Yeah, I believe also that it is run like a normal programming language too. So, and last one has nothing to do with it, but just want to show you. Yeah, it is the print hello world, but printing it conventionally. So notice that I used unit as the return value. It means like there's no value expected in this case. We're just doing the message hello quantum world. And that's all. Any more questions?
Could we see the histogram for example 2?
Yes. Histogram, yeah.
It likes its zeros.
Yeah.
It's like zeros.
Yes. And then I should also show the circuit too. So I'm gonna quickly close the file explorer here. So there we go.
Yeah.
Yeah. So notice we have 2 qubits this time. So we're doing the head-MRD operation on the first one, and we're entangling that one with the second one. We're measuring and then resetting both.
But I noticed, or I can tell this
is language written by mathematicians and not programmers, because all the functions are H and M instead of system.diagnostics or system.
They're not very verbose,
No.
yeah.
If you want a language written by mathematicians, look up Haskell.
Yeah. Haskell will do it. So, I'm assuming the circle with the plus in it is the like an entanglement, like showing that it is entangled within the like circuitry there.
Yes.
And I don't know if this is beyond scope of this, but I guess what's like the practical application for entangling two qubits? Like, what would you use that for in like a quantum program?
Because in real quantum systems, you might entangle something with something else, so you can do multiple operations.
Sorry.
Gotcha.
It extends, well, some of the practical applications are it extends the range of communications.
Mhm.
They've been able to entangle photons and then separate them, I think on the order of tens of kilometers.
Oh,
Currently,
wow.
and
they
get-
would,
yep.
oh, okay.
Yeah, so you change it here, and then in the lab, across
Yeah.
campus, it's changed over there. So if you could do that in the program,
Yeah.
then,
Yeah. And I'm assuming it's pretty instantaneous.
Yeah.
Yeah.
It's, Einstein called it spooky action at a distance, or something
Yeah,
close to that.
I feel like that feels pretty accurate. Yeah.
Yeah. So theoretically, they could be on opposite sides of the solar system, and you flip one.
Instantaneously flip.
Yep. Theory.
Yeah.
Yeah, and I quickly looked up some things to listen to while on the way here, and one interesting news is that because in real quantum computers it can get messy and interfere with the actual results, the researcher reasoning 5 quantum qubits to make like one logical qubit.
It's almost maybe like a error checking ECC
Yes.
in quantum.
Mhm.
That makes sense too. Yeah. Yeah, because that would fight your noise and anything that might possibly flip it.
Right.
Because the other ones would resist the flip theoretically.
All right, any more questions?
So I'm guessing when NASA's using this and Jefferson Labs.
Yeah. I think Jefferson Labs probably is running some of these simulations on their supercomputer realistically.
Yeah, and NSA is like looked at quantum computers, like I said, to crack encryption. And yeah, I think there was like one presenter a while back for this group who was talking about like quantum proofing our encryption software.
Mm-hmm. It was about 2 or 3 months ago. He gave that presentation on rather than using RSA keys and the current SSL technology to encrypt web traffic, he would use quantum resistant encryptions. Because the theory is once you crack quantum computing, then factoring insanely large numbers becomes trivial.
Yeah.
And so all of our current encryption technologies are null and void.
Yeah.
So NIST has been trying to get ahead of this for a very long time now.
Yeah.
They just upped the timeline. Google updated the timeline that they're going to embrace the quantum. I forget what it's called, but the quantum RSA replacement by 2028 or 2029, which is a couple of years ahead of schedule because they think it's going to come faster than anticipated. And the problem is NSA has been capturing all the encrypted data it can get its hands on.
Yeah.
So as soon as this becomes available, they'll be able to
Crack
decrypt anything. So.
Yeah, and I think the day is coming where every single university and major corporation would have like their own quantum computer.
Yep.
It feels very much like the like MIT first computer days, where it took up an entire room, and then one day we're all gonna have a quantum computer in our pocket.
Yeah. Yeah. It'll just be our phone.
Yeah. iPhone Q37.
What have you used it for?
I'm just looking at because like I have a few different things I want to see what it can do. Yeah. Right now I've been interested in like Shor's algorithm, which if you don't know is like the algorithm that someone made up for quantum computers to break quantum encryption by factoring a very large number very fast. And I'm also looking at what other ways that we can use quantum computers, because I thought of like, can we also use them to render graphics? Because like if you don't know, there's a very simple algorithm to do graphics called ray tracing. Which is like simple to understand, but it's
Hard to
actually
calculate.
pretty complicated to do on the computer, and I think that just now they're able to do it live. So I want to see if it's possible to use quantum computers for that.
Ray tracing, if anyone's unaware, is kind of trying to emulate the same concept of lighting in our real world. So like we turn on a light source, photons of light come from the light bulb and illuminate all of this space, right? Like we turn on some lights, we get more light, we turn some off, they get dimmer. How they hit a certain surface reflects a certain way. So ray tracing is trying to emulate that one for one inside of a computer realm. So you'd have light sources that shoot the photons out, they bounce around the entire area of wherever 3D space you have, and that's how you get that illumination and lighting in certain areas, instead of like just kind of cranking like colors up in certain areas and down in certain areas manually. So you get better pictures, but it's really hard to calculate since you're literally trying to calculate how a photon is bouncing around in the room. So yeah, I think that'd be kind of an interesting concept.
Yeah,
You could
and
do that
then
work.
another good use for quantum computers is like essentially predicting the the properties of a molecule, because that's hard to do with a regular computer. So it'll be like much easier on a quantum computer.
Yeah, I saw it was being used for protein folding as well.
Yes.
For what?
Protein folding, which
yeah.
is like one of the big ways that they're trying to find new medicines and tackle like fighting cancer, finding solutions to that is through protein folding. Like currently, it's run through a bunch of big supercomputers, and there's also a couple kind of more DIY open source home labby type styles where you can run a program on your computer to kind of contribute some of your computer's resources to like a big shared networking pool.
A SETI at home type thing.
Yeah.
Folding at home.
Folding at home.
Folding, yeah.
Linus Tech Tips on YouTube's done a bunch of big pushes to try to get people to do like they do like a month where they get a bunch of their viewers to sign up as well, because they're a bunch of computer nerds too,
Right.
and get those systems to help try to progress some of that research forward.
This is interesting though.
Yeah, and it's also cool you can play with it locally some too.
Yeah.
It's a little more hands-on than last time I saw a quantum computing talk.
Yeah, personally, I've also looked into Qiskit as well, and I prefer this over Qiskit.
Have you gotten to run anything on like the actual hardware? How cost prohibitive is that? I feel like it's pretty
No, I've
high.
actually been busy with like personal stuff
Yeah.
recently, so I haven't been able to do that.
You said this was running on container and Azure, right?
Yeah, I can quickly show you that. Let's see if I can. Okay, there we go. Yeah, here's my Quantum workspace. Notice this name right here.
Yep.
And nice things like when you go into like the VS Code, they already have a whole bunch of example programs to go through. And I'm not gonna go through all of them, some because there's a whole bunch. So I encourage anyone to look through them if you're interested. See. Okay, yeah, Shores. They have Shores algorithm. Let's see that. And yeah, here is like their implementation of Shores algorithm, which like I said before, is the quantum algorithm for factoring big numbers.
It's so small.
Yeah, let me.
No, it's just the algorithm itself is. I was expecting more.
Yeah,
More
it's
verbose.
pretty.
Yeah, most of the verbosity is just in comments.
Yeah.
There's more comments than actual code.
Yeah.
Well, I love number factorization. I've always been fascinated by it. So, you know, all the modern factorizations are except for the most trivial ones, are
Yeah.
large and intense.
Yeah.
That's what I do on mine. I use the GIMPs, Great Internet Mersenne Prime Search, which are the largest prime numbers in existence.
Yeah, so I know that like yeah, everyone here is not a quantum physicist, so I tried to be as like basic as possible just to get my point across. Hopefully I succeeded
Yes.
today with that.
Yeah. Thanks for the talk.
Yeah, I learned a lot.
Yeah.
Good job, Al.
Let me turn off the recording.
You want me to get it?
Yeah.
I think, nope, I did not get it. You can get it.
Okay.